Okay, so we begin. Good morning, everyone. Hope you survived your first week of college. Okay, so I presume everyone, most people here are still here, so most of you presumably survived your first week of college. So congratulations. Just a few quick announcements. I'm just going to reuse the same slide from last time because there's pretty much nothing new I need to say. Homework 2 has been extended to tonight at 11 p.m. Homework 3 is also due tonight at 11 p.m. And the extra credits is also available until 11 p.m. tonight. And so please make sure you do the extra credit as well because it's a super easy way to get 2 extra credit points in like 2 to 3 minutes. So please make sure you do that as soon as you can if you have not done so already. And quiz 1, as I mentioned, is going to be 9 a.m. on Wednesday, September 2nd to 9 a.m. on September 3rd. You can take quiz 1 anytime within that window. And it's a 10-minute quiz, so it doesn't take too long. And it covers lessons 2 and 3. So just so you know what to look out for in that quiz. So that out of the way, does anyone have any quick questions on the homework or anything due tonight? All right. Then let's talk about finding limits analytically. Okay, so let's recall this definition from last time. So, actually, sorry, before I do, I don't have to keep awkwardly looking at the projector every 5 seconds. Okay. Alright, so recall from last time. We have a function is continuous at x equals c if 3 criteria are fulfilled. So we have that f of c, first off, has to be defined. That's criteria A. Criteria B is that the limits as x approaches c of f of x, that has to exist in regards to the two-sided limits. And then part C, as I said most importantly, the limits as x approaches c of f of x has to equal f of c. Okay? So that's just a definition we had from last time. So one implication we can get from this is the following. So if we take a look at this property C here, then what we'll notice is that if we have a continuous function, then if you want to find the limit here, sometimes it might just suffice to find the function value at that point. So that's one nice thing that continuous functions let us do. So the implication is that depending on f of x and c, the value of c, not the property c, we may only need to consider f of c to find the limits as x approaches c of f of x. Or in the case of piecewise functions, the one-sided limits. Or limits as x approaches c from the left of f of x. Or limits as x approaches c from the right of f of x for piecewise functions. Okay. So that's that. So now it's good to know that we have this property to let us simplify dealing with limits here, but what are examples of continuous functions? By which I mean functions that are continuous at every point on their domain. So let me write that down. So I'll say continuous. So when I when I say CTS, that's going to be my shorthand abbreviation for continuous in this class. So just so you guys are aware of that. So continuous at every point in domain. Okay? So that's all that continuous functions mean. So first one is we have polynomials. So 2 is exponentials. Three is trig functions. Rational functions. And when I say rational functions, I mean like one function divided by another function is what I mean by a rational function. So p of x divided by q of x. Actually, q of x. Okay, it's a bit cleaner. 5 radicals, by which I mean square root of something, cube root of something, etc. And then the last thing is logarithms. Okay. Now, keep in mind, polynomials and exponentials are are usually defined everywhere on the entire real line. So that means for every real value of x that I want to pick, you can usually find the corresponding function value. But for the other three, sometimes their domains may be restricted. So for instance, with, say radicals, for square root, you can only have x greater than or equal to 0 here. Or with logarithms, as I mentioned in lesson 1, you have to make sure whatever's inside your logarithm has to be strictly positive. So just a couple of examples of what I mean by that. So these are going to be continuous on their domains. Okay. So those are examples of continuous functions. So any questions on any of that before we move on to example 1? Okay, so the first thing we're going to do is we're going to consider limits of non-piecewise functions. So in total, there are essentially three cases for dealing with them. So the first case is that if f of c equals some finite number. So here, you can just say the limit of as x approaches c of f of x is simply going to correspond to f of c. So usually in this case, you'll end up corresponding to some nice continuous function. All right? So here's what I mean by that. So for example 1a, for instance, let's let f of x here be 4x minus 3. So let this be f of x. So what happens here is that if I let f of x equal this, and I want to consider f of, say, 3, then all I have to do is say, all right, well, f of 3 is just 4 times 3 minus 3. And that's just going to be, 12 minus 3, so that's just 9. But the good news is that this is just a nice finite number. So in this case, you just end up with the limit as x approaches 3 of 4x minus 3 will just be 9 here. So the thing is, you could have done what we did in lesson 2, pick values of x really close to 3 from either direction and deduce a limit value from that table. But in this case, since we have a nice continuous function, we can just let our limit value equal the function value and we're good to go. Okay. Now if the limit as x approaches 0 of x divided by x plus 4, so that's going to be a similar idea. So in this case, if we let this be f of x here, then using the same reasoning as part A, what should we get as our limit value? Yeah, we should just get 0, right? Because f of 0 in this context is just 0, which is, again, a nice finite number. So, 0 here. So, nothing too wild or crazy there. So, any questions before we move on to example 2? All right. Okay. So that's case 1. Now case 2 is where things get a little bit more crazy. So f of c, or case 2, is going to be a non-zero number, divided by 0. So here is where things get a little crazy, because in this case, as you'll see in examples A and B, there's not really much you can do to simplify these. So you're kind of just stuck with whatever is happening downstairs with x equals, with their denominator equaling 0. So unfortunately, the only thing we can really say on this is that the one-sided limits are going to end up being plus or minus infinity. Okay? So use these to find the two-sided limit, the limit as x approaches c of f of x, by using numerical methods from lesson 2. Lesson 2. Okay, so here's what I mean by this. So for example 2a, if we let this be f of x, then you realize, wait a minute, f of negative 4, well, that's just going to be negative 4 divided by 0. And so unfortunately, you're kind of just stuck with the 0 downstairs, and there's nothing you can really do to cancel it. So you just kind of have to put up with the 0. So as we mentioned in this explanation here, all we have to do is just first focus on the one-sided limits first and see what we end up with after that. So negative 4 from the left of x divided by x plus 4. And then the limits of as x approaches negative 4 from the right of x divided by x plus 4. Okay? So as I mentioned in this explanation here, the one-sided limits are going to end up being plus or minus infinity. So in this case, if we have to use numerical methods from lesson 2, what I mean by that is that all we have to do is just pick, in this case, 1 or 2 values that are close to negative 4 from the left and right, and see what sign they carry to help us determine whether it's plus or minus infinity. So let me write that down. So for the left side limit, for instance, so pick 1 or 2 values. Pick 1 or 2 values close to negative 4 from left. For example, negative 4.1, and find sine of f of negative 4.1. So in this case, if we replace x in here with negative 4.1, then what do we end up with? So should we end up with something positive or something negative? So if we just if we replace negative if we replace x with negative 4.1 here and here, should we end up with something positive or something negative? Negative? Positive, right? Because you have negative 4.1 here divided by negative 0.1 down here. So that should end, you should just end up with, well, 41 if you want to put that into a calculator, which should end up being positive. So in this case, you end up with, because this is a positive value, you're going to end up with positive infinity here. Okay? Okay. So now let's do the same thing with the right side limits. So in this case, pick a value. Pick a value close to negative 4 from the right. So in this case, what x value would you want to pick here? Negative 3.9, just using the same reasoning as first limit here, first limit, and find sine of f of negative 3.9. Okay? So what would that be here? This is just negative infinity? Well, just replace x with negative 3.9 here. So you have negative 3.9 over what? So you have something negative on the top here, but then you have something, will this be positive or negative down here? Be positive. So you have something negative divided by something positive, so that should end you up with something negative here. So, and if you want to plug this into a calculator, you should end up with negative 39. Okay? So in this case, that'll end you up with what for a right side limit? Positive or negative infinity? Yeah, negative infinity. Good. But wait a minute. These two are not the same, are they? So what should that tell you about the general two-sided limit here? What's that? Right, doesn't exist. Good. And abbreviate as DNE. Okay. So that's part A. Now let's do the same thing with part B. So we have 1 over x squared here. So as before, we're going to have, if we let x equal 0 here straight away, we're just going to have 1 over 0. So we again have to deal with the one-sided limits here again. So again, focus on the limit as x approaches 0 from the left of 1 over x squared, and the limit as x approaches 0 from the right of x squared. Okay. So in this case, let's do the same thing that we did in the last part and pick two values close to 0 from the left and right that will help us give us the sum. So for the left side limit, what value of x would you want to pick here? So what value of x that's slightly less than 0 would you want to pick here? Okay, negative 0.1. Okay. And then by similar reasoning, let's use x equals positive 0.1 for the right side limits. So f of negative 0.1 is going to end up being what? Something positive or something negative? Positive, right? Because even though you have a negative here, this x squared on the denominator is going to get rid of that negative for you. So In this case, if you plug this into a calculator, you'll get 100, which is greater than 0. And then if you do the same thing with positive 0.1, well, luckily you're going to get the same exact value here. So, which will also be positive. So that means that your one-sided limits will both be what? Positive infinity, good. And hence your desired two-sided limit will be someone else. What would the two-sided limit be, given what we have? Just infinity, good. So that's all I wanted to say on case 2. So any questions on that? Alright, cool. So case 3 is the last thing I want to talk about. And what that says is that if we have something like f of c equals 0 divided by 0. So just by this alone, there's not much we can do to analyze the function value. So we have to use some sort of algebraic manipulation to figure out our limit here. So use algebraic manipulation to properly find limits. So that's case 3. So let's use that reasoning on part A here. So if we're asked to find the limit as x approaches 0 of x squared minus 7x divided by x squared plus 10x, well, if we let this be f of x here, then f of 0, well, that's just going to yield 0 divided by 0. So, unfortunately, there's not really much we can do to analyze the function value here. But what do we notice from this? Well, if we plug in 0 in the numerator, well, that'll give us that the number 0 is a root of the numerator as well as the denominator. So, maybe there's something we could factor out of top and bottom to see what our desired limit value is. So, however, so x squared minus 7x divided by x squared plus 10x. So if you notice, both the top and bottom carry a factor of x on them. So let's go ahead and factor them out and see what happens. X and then x plus 10. So all I did was I just factored out a factor of x on top and bottom. So remember, with limits here, we're taking the limit as x approaches 0, so x can't actually equal 0 here. So for x not equal to 0, so because of this, that means we can safely cancel out these factors of x that are getting in the way of finding the limit value. So ultimately, we end up with x minus 7 over x plus 10. So all that means here is that if you want to find this limit here, all we have to do is figure out the limit as x approaches 0 of x minus 7 divided by x plus 10. So if you just let x equal 0 here, what you notice is that you essentially just get to a case 1 style limit, in that you can just plug in x equals 0 straight away, and you're good to go. So in this case, your corresponding your corresponding limit for your answer here will just be negative 7 divided by 10. If you just let x equal 0 in your function. So that's part A. So any questions on that? All right. Now let's use the same reasoning on part B here. So, again, we'll have to let x equal, well, f of x equal this function here. So again, f of 1 is going to be 0 divided by 0. So that means that, again, we should have that 1 is going to be a root of the top and bottom. So let's see what we can get rid of on the top and bottom to make things a little bit nicer. So x squared plus 2x minus 3 over x squared plus 5x minus 6. So since we have a quadratic, that means we should be able to factor this out into two factors on top and bottom. So on top, we should be able to factor that as what? So what can we factor? Go ahead.
X plus 3 and then x minus 1.
X plus 3, x minus 1. Good. And then the bottom?
X plus 6 and x minus 1.
Yep, x plus 6 and x minus 1. Good. So now in this case, we're letting x approach 1 here. So that means all that says is that we cannot let x equal 1. X cannot equal 1. Or to be slightly more consistent with what we saw in part A, or x minus 1 cannot equal 0. So what that means is that, as in part A, we can safely cancel out a factor of x minus 1 on top and bottom to find a limit here. So we have x plus 3 over x plus 6. Okay? So what that says is that this limit here is the same thing as trying to find this limit here. As x approaches 1 of x plus 3 over x plus 6. So using the same reasoning as part A, we should end up that this limit is what? 4 over 7. Good. Because in this case, you can just let x equal 1 here without any repercussions. So you get 4 over 7 here as your desired limit value. Okay? So any questions on example 3? Alright. So that's all I really wanted to say on the non-piecewise functions. So now let's turn our attention to piecewise functions. Let's do this. So suppose we are given f of x below. So we have f of x equals 8 times the square root of x plus 3, provided x is not equal to 9. And if x equals 9, then we just simply have 17. So using this, let's find the following values. So we have to find the one-sided limit as x approaches 9 from the left. The one-sided limit as x approaches 9 from the right. And then the corresponding two-sided limit as x approaches 9 of f of x. And then the function value at x equals 9. So let's start with the easy one. So if we have that x equals 9, then f of 9 should equal what?
17.
Yeah, 17. And that straight up comes from our way we constructed our function here. So if x equals 9, then f of x equals 17. So nothing too crazy with that. So now let's move on to A through C here. So part A, so limits as x approaches 9 from the left of f of x is going to end up being what? So here, remember with limits, we have to make sure that we have to use values of x slightly, use values of x slightly less than 9, but, and then in all caps, not equal to 9. Okay? So, using that says, all right, so with that being the case, which of these two pieces of f of x should we be using in this context? So we want to make sure we're slightly less than 9 while also being not equal to 9. So which of the two pieces of f of x will let us work with that? Top one, right. Because in this case, we just want to make sure we're not equal to 9. So the only one that lets us do that is this top one here. So the limits as x approaches 9 from the left of f of x is the same thing as the limit as x approaches 9 of 8 times the square root of x plus 3. Okay? So now here, the fact that we have to make sure we're not equal to 9 only really comes into play in going from here to here. Going from f of x to some explicitly defined function. So from here, we're just straight back into the non-piecewise function case. So if we were to say let x equal 9 straight off the bat, then let's see what happens. So we have 8 times the square root of 9 plus 3. So if that's the case, then if you simplify all this, then you should end up with 8 times 3 plus 3, which is 27. So going from here to here, we need to make sure we're not equal to 9. So that's where the limit part comes into play. But once you get to here, we're back in non-piecewise function land. So in this case, we end up with a case 1 style limits. So you can just let x equal 9, and that'll give you your function value or your limit value straight away. Okay? So any questions on that? All right. So now part B is going to be similar. So the limits as x approaches 9 from the right of f of x. So we're going to need to use similar reasoning here. So use values of x slightly less, slightly greater than 9, because we're working with a right-sided limit now, than 9, but then in all caps, not equal to 9. All right. So using this reasoning, which of the two functions here should we be using in this case? Using similar reasoning as part A. So in this case, we need to make sure we're not equal to 9. So in this case, since the only part of the function that lets us work with x not equal to 9, well, we should probably use the top one here. So the limit as x approaches 9 from the right of 8 times square root of x plus 3. So this limit of f of x is the same thing as the right side limit of 8 times square root of x plus 3. So with this being the case, that should tell you that your right side limit is going to be what? Again, using similar reasoning as part A. 27, good. So 8 times square root of 9 plus 3. You can just let x equal 9 here because that's allowed in your domain. So at least for this function. And then that just gives you 27 here. Okay? And then part C, based on what we have for parts A and B, the corresponding corresponding two-sided limits should be what? Good, just 27. Alright, so that's all I wanted to say on example 4. So any questions on that? Okay. So the nice thing with this example is that all we really had to make sure of is that x was not equal to our particular value. So in this case, the one-sided limits corresponded to the same function, or at least the same part of the function. But in example 5, as you may have seen already, we have to be a little bit more careful. Because now we have 3 parts, each of which correspond to, we have to correspond to a specific direction for each of our functions. So in this case, which I mean by that, is that if x is less than 0, then f of x is x squared plus 3, and then 4x minus 1 if x is in between, is x if 0 is less than or equal to x and less than 1. And then if x is greater than 1, then we have 4x squared plus sine of 3x divided by 2 times x. Okay? Alright, so with that being the case, let's go ahead and start by finding part A here. So part A, the limits as x approaches 0 from the left of f of x. So in this case, we're going to need to make sure we're, again, staying relatively close to 0 from the left while not actually equaling 0 here. So using that reasoning, which of these 3 functions should we be using? Yeah, top one, right? Because for part, like we said, the left side limit means we have to use values of x slightly less than, but not equal to, in this case, 0. So the only part of the function that lets us do that is the top one. So the limit as x approaches 0 from the left of f of x is the same thing as the limit as x approaches 0 from the left of x squared plus 3. Okay? So now once we are here, we're basically back in non-piecewise function land again. So in this case, x squared plus 3 is just a nice polynomial that's defined everywhere. So our function value there should be what? Our limit value should be what? Yeah, just 3. Because all you really have to do is just let x equal 0. And then that just gives you the limit value of 3 here. Okay? Okay. So that's part A. Part B, let's find the limit as x approaches 0 from the right of f of x. So in this case, again, use values of x slightly, in this case greater than, and then again, but not equal to 0. So in this case, which of these 3 pieces of f of x should we be using in this case? Second one, right? Because that's the only one that lets us stay relatively close to 0 while still also being greater than 0. So in this case, use the limit as x approaches 0 from the right of f of x is the same thing as limit as x approaches 0 from the right of 4x plus 1. No, sorry, minus 1. Sorry. So in this case, you should end up with a limit value here of what? What would your limit value here be? Let's give someone else a chance. So in this case, we again have a polynomial here, so it looks like we have a case 1 limit. So what would our limit value here be? Negative 1, right? You just have 4 times 0 minus 1. That's just negative 1. Okay? So, with these two one-sided limits in mind, that should tell you that the general two-sided limit here is then going to correspond to what?
Does not exist.
Doesn't exist, right? Because the one-sided limits do not agree with each other. Good. Okay. And then for part D, all we really need to do here is just focus on f of 0. So in this case, we are actually letting x equal 0 here. So which of our 3 pieces should we be using in this case? Second one, right? Because that's the only one that actually lets us deal with x equals 0. So we have 4 times 0 minus 1, which is just negative 1. Okay? So that's parts A through D. So now let's do the same thing, except instead of letting x approach 0, or x equals 0, depending on which part you're looking at, let's repeat the same process for x equals 1. So for part E, limit as x approaches 1 from the left of f of x. So which piece of f of x should we be using in this case? Second one, right? So that's the only one that lets us stay relatively close to 1 without being actually equal to 1. So in this case, x equals 1 from the left of f of x is the same thing as the limit as x approaches 1 from the left of 4x minus 1. So our limit value there should be what? 3. Yep. Alright. And part F, limit as x approaches 1 from the right of f of x. So in this case, that's the same thing as saying limit as x approaches 1 from the right of what explicit function? Someone else? So which piece of f of x should we be using in this case? Bottom one, right? So in this case, we just have 4x squared plus sine of 3 pi over 2 times x. So the nice thing is that here, well, we just have one function which is defined everywhere as a polynomial, and sine is defined everywhere. So we just have 4 times 1 squared plus sine of 3 pi over 2. So the nice thing is that, well, the first term is going to simplify to 4, no problem. But what about the second term? What does that equal to? Negative 1, right? Remember, so this is where our unit circle has to come into play here. So that's 3. Okay. And then G, because our one-sided limits are the same, that gives you that the general two-sided limit will also equal that value, so that's just 3. And then for H, all we have to do is let x equal 1 straight off the bat. So using that, so this is a value we're trying to find. What would our value in this case be? 3, right? Because in this case, you'll want to use the bottom one because that corresponds to when x equals 1. So in this case, you'll have 4 times 1 squared plus sine of 3 pi over 2, which is just 3. Okay, so that's all I wanted to say on that. So do you guys have any questions on that? Okay, cool. Then I will see you guys on Wednesday. Keep in mind, I will have Zoom office hours tonight from 6 to 7, and I'll send out a Zoom link shortly after class. So just so you guys are aware of that. Otherwise, I will see you guys on Wednesday. Oh yeah, also, please make sure to wipe down your tables before you leave.